Welcome to day 33 of our STL course. Today we are going to explore one of the most powerful combinations in algorithmic problem solving, STL and backtracking. Backtracking is an elegant technique used to explore all possibilities for solving problems with constraints. We will see how STL containers like vectors, sets, and maps can help us simplify and optimize these solutions. By the end of this session, you will be ready to apply these techniques to problems like generating subsets, finding permutations, solving n-queens, and even Sudoku puzzles. Let's dive in. Before we dive into backtracking, let's quickly refresh our understanding of recursion. Recursion is a method where a function calls itself to break down a problem into smaller subproblems. Every recursive solution has two critical parts: the base case, which stops the recursion, and the recursive case, which keeps breaking down the problem. Understanding recursion is crucial for solving problems with backtracking because it allows us to explore different states and systematically undo our decisions when they lead to dead ends. Backtracking is a powerful technique for solving problems that involve searching through all possible configurations. Rather than blindly trying each option, backtracking helps us prune the search space by abandoning paths that are invalid or unpromising. It's like navigating a maze and only moving down paths that could potentially lead to the exit. If you hit a dead end, you backtrack and try another path. This allows us to focus on more promising options without wasting time on fruitless paths. Backtracking is perfect for constraint-based problems like n-queens or Sudoku, where you need to satisfy certain conditions at each step. Now let's look at how STL containers come into play with backtracking. STL provides a wide range of containers that help us manage the state of our solution as we explore different paths. For example, vectors are great for dynamically building and removing elements as we generate subsets or permutations. Sets help us track states that we have already visited, ensuring that we don't waste time revisiting the same configuration. Maps, on the other hand, are helpful for memorization, where we store previously computed results to avoid redundant work, and we can even use stacks to simulate the recursive call stack in iterative backtracking algorithms. Subset generation is a classic backtracking problem. We want to generate all possible subsets of a given set of elements. To do this, we recursively decide whether to include or exclude each element from the current subset. Using STL vector makes this process efficient and straightforward because we can easily add or remove elements. With every recursive call, we explore one possible subset configuration, and if it's not valid or promising, we backtrack. The vector allows us to dynamically adjust our subset as we explore different paths. Here's the code for generating subsets using recursion and STL vector. Each recursive call will either include the current element or exclude it, and the results will be stored in the vector. Notice how easy it is to push and pop elements from the vector, which makes it a perfect fit for backtracking. This approach ensures that we explore all possible subsets efficiently. Another classic problem where backtracking shines is permutation generation. In this case, we need to generate all possible arrangements of a set of elements. We start by fixing one element in the current position and then recursively generate permutations for the remaining elements. STL vector helps us manage these arrangements in place, and backtracking ensures that once we explore one permutation, we revert any changes and explore other options. This is a great example of how STL can make recursive algorithms both simple and efficient. Here's a code snippet for generating permutations using STL vector. The key idea is to swap elements into the current position, recurse, and then swap back to undo the change. This process is repeated for all elements. STL's vector simplifies this task by providing dynamic array-like behavior, and the swap function is used to manage the element's position. Notice how this approach avoids the need for extra memory allocation, which makes the algorithm both time and space efficient. Now let's move to a more complex example, solving the n-queens problem using backtracking. In this problem, we need to place n-queens on an n cross n chessboard in such a way that no two queens threaten each other. We use a vector to track the positions of the queens on the board, and we use sets to track which columns and diagonals are already occupied. This allows us to quickly check if placing a queen at a particular position is valid. The power of STL lies in how it helps us manage the state of the solution efficiently and avoid redundant calculations. Here's a code for solving the n-queens problem using backtracking and STL containers. We maintain three sets, one for columns, one for the first diagonal, and one for the second diagonal. These sets allow us to efficiently check if a queen can be placed at any given position. After placing a queen, we recurse to the next row. If we reach a point where no valid position is found, we backtrack and try another column. STL makes managing the state and checking constraints much easier. Now it's your turn to practice. Try implementing recursive solutions for these problems on your own. Start with generating all subsets of a string. Once you are comfortable with that, move on to generating permutations, making sure to handle duplicates properly. For an additional challenge, try solving Sudoku using backtracking or implement a word search solver. These problems will really test your understanding of recursion and backtracking combined with STL. To summarize, today we have seen how STL containers like vector, set, and map can be used to simplify backtracking algorithms. These containers help manage the state, track constraints, and make the code cleaner and more efficient. Backtracking is a powerful technique for solving many types of constraint-based problems, and STL helps you implement these solutions quickly and easily. Next up, we will be diving into some advanced practice problems. This will challenge your skills in STL, recursion, and backtracking, and are perfect for preparing for coding interviews and competitive programming contests. Get ready to solve complex, real-world problems that combine multiple techniques in interesting ways.